So far we have talked about the ideal gas law in many respects. We have said that the PV equals nRT contains Boyle's law, Charles' law, Avogadro's law, Gay-Lussac's law that we didn't talk about, but it's also another law that PV equals nRT contains. We also have talked about the idea that this N refers to a number of moles, and the number of moles may be equal regardless of the gas. However, when we talk about grams, then the identity of the gas has to be taken into account. The other aspect of ideal gas law that we're going to talk about is this time is in case of mixtures. So the ideal gas law is also very interesting when it comes to mixtures. When you have a mix, several substances, several compounds in the same gas, in which you have certain number of moles for one gas, certain number of moles for the other gas, certain number of moles of the other gas. Of course, the total number of moles will be the addition of the different moles of the gas. So the good thing is that one can write the ideal gas law. This will be the overall pressure, and this will be the total number of moles. So say that you have a container with just air. As you will know, that in air you have nitrogen and you have oxygen, you have some CO2, you have some argon, you name it. If you add up all of the moles of gases, regardless of their identity, you can still apply ideal gas law. This is why it's ideal. Ideal gas law does not care about the identity of the gas. Therefore, what you measure is the total pressure. Okay, what you measure here, if you put here the total number of moles regardless of its identity, you're gonna measure the total gas, the total gas pressure, excuse me. All right, in this case, if it's atmospheric pressure, it would be 1. Okay, the cool thing though is that you can just substitute this in here, and of course then you would have something like that. Applying the distributive property, what you could do is that you would end up getting with tiny ideal gas laws for each of the component, so that the total pressure would be equal to what we call partial pressure, the partial pressure for each of the component. Alright, so in this case, in our example of having just a container with air, you would have a partial pressure of nitrogen, which would be equal to the number of moles, in this case of only nitrogen, R, temperature, and volume. Of course, temperature and volume are common to the whole container, so they don't have to have the subscript of nitrogen here. And the same could be said. Oxygen is equal to the number of moles of oxygen, RT, divided by the volume, and so on with the rest of the components, so that the total pressure in this container that we have drawn up here would be the pressure of oxygen plus the pressure of nitrogen plus the pressure of CO2, each of them calculated with their own tiny or pet ideal gas equation. Alright, so you can apply the ideal gas law to the whole mixture, but you can also apply ideal gas law to each of the specific component, as long as you include the number of moles of that specific component. So let's solve a problem and let's see if this is making some sense. For example, in this case, it's asking for the partial pressure of neon in a mixture of neon and xenon. So they are all noble gases, so they're going to behave ideally. They do not interact with each other. What it's saying is that the total pressure is 3.9 atmospheres and the volume is 8.7 liters, and the temperature is 598 Kelvin. And here it's telling you already that the number of moles of xenon is 0.17 moles. So wait a minute. If we can apply the ideal gas law for each of the component, and we already know volume, temperature, and number of moles for xenon, it means we know the total the pressure of xenon. So we could write pressure of xenon is equal to the moles of xenon, RT divided by V, and of course the same can be said for neon, right? Neon RT divided by volume, and the same could be said about the total pressure, the total number of moles RT divided by volume. Alright, what it's asking here is the partial pressure of neon. We want to know this, but careful, because we do not know the number of moles of neon. What we know, okay, is that we can calculate the partial pressure of xenon. Partial pressure of xenon, that we know, 0.17 times point, that's the value of R. Let's put the atmospheres liters, mole Kelvin. It's 598 Kelvin divided by the volume, 8.7 liters. Okay, this will give us a number. Okay, notice that it's telling you that the total pressure is 3.9. The total pressure is equal to the summation of partial pressures of xenon plus partial pressure of neon. Alright, we know that the total pressure is 3.9 atmospheres, and the partial pressure of xenon is what we just calculated up here. I do not have a calculator right now, so I'm going to call this number A, okay, which I know. Just need to plug it into a calculator, and this is what I need to know, partial pressure of neon. Therefore, the partial pressure of neon is equal to 3.9 atmospheres minus A, which is the value that I calculated here. Therefore, I can find the partial pressure of neon, even though what they have just told me is the partial pressure of, well, what I have calculated is just the partial pressure of xenon. Hopefully that makes some sense.